Yeah, now we're live on YouTube also. Welcome to the Tartaglia seminar at the Physics Institute of the Autonomous University of St. Louis. Today, we are happy to receive Professor Gabriel Fuhrmann from Durham University, UK. After obtaining his PhD at Friedrich Schiller University, Professor Fuhrmann has focused on several areas in dynamical systems, including one-dimensional dynamics, iterated function systems, and symbolic dynamics, among others. His work has been published by very important journals such as Organic Theory and Dynamical Systems, Transactions of the AMS, Discrete and Continuous Dynamical Systems, and many more. Today, Professor Fuhrmann will present his work entitled Non-Timeless Among Tuplet Shifts, and thank you for participating with us.
Thank you for the invitation and the nicest introduction I ever had for a talk. Thank you. I'm going to talk about non-timeless in the class of so-called tuplet shifts, and this is a joint work with the people whose names appear at the bottom of the slides: Johannes Keindonk and Rina Zabi. And I will try to, at least to a large extent, to be as basic as possible so that everyone is on the same page. If at some point you feel like I should clarify something, something is just completely unclear, please interrupt me and ask for clarifications. I will start with some very basic notions where I hope that everyone actually is familiar with them, just to ensure that we really share the same language. So what this talk is about dynamical systems, in particular topological dynamical systems, which are nothing but a compact metric phase space X and some continuous self-map on this phase space, okay? Actually, later in the talk, I don't want to consider homeomorphisms. I wrote homeomorphisms here. It doesn't really matter, in fact, for the content that I will present or for the actual statements, but it matters a bit when it comes to the presentation of some arguments, which I will discuss later, and they are actually easier to be discussed if we allow for a more flexible notion. So not just homeomorphisms, but continuous self-maps on compact metric spaces. Okay, and then we say such a dynamical system is minimal if every orbit is dense. What is an orbit? Just in case you don't know, say given a point X in X, its orbit O of X is nothing but the set of all its iterates, okay? Where n, well, if we have a homeomorphism, n is an integer, and otherwise it is just a natural number. Okay, so if every such orbit is dense in our space X, then we say the system is minimal. In fact, well, the core results that I will present today only deal with minimal systems. So, well, we will also make use of non-minimal systems, but basically you can always consider the systems to be minimal in this talk. Okay, then the next very important notion that we will also make use of excessively is that of a factor or of an extension. So given two systems, our system F on the space X and another system G, or another self-map G defined on the space Y, we say F is an extension of G, or G is a factor of F if this diagram commutes, okay? I assume that everyone is familiar with that as well. And this I already said. And in case that this map pi, this factor map, in case this map pi is not only continuous, it's always continuous and onto, but it's not, if it's not only continuous and onto, but also injective. So in other words, if pi is a homeomorphism, these two systems, XF and YG, are topologically the same, and we say they are isomorphic, or also they are conjugate. Okay, I assume that everyone is familiar with these notions. If not, please shout. Then we proceed to something maybe a bit more special, but still not too advanced, the so-called Ellis semigroup. So given a dynamical system XF, we can always associate a semigroup, a topological, and not a topological, almost topological semigroup, to the system XF by, well, we denote this by E basically, so forget the left-hand side, by taking the closure of all the iterates of our map F. Okay, assume, well, if F is a homeomorphism, then all the iterates are also the backwards iterates. If F is just a continuous self-map, you would have to replace the Z by an n here, right? Okay, so our LS semigroup is nothing but taking all the iterates of our map F and taking the closure in the topology of pointwise convergence, which is nothing but well, the product topology on the map of on the space of self maps from X to itself. Okay, and of course, taking the closure and the product topology is a very rough thing to do, and you basically lose, or you can potentially lose all the properties of all the nice properties of the map F that you start with, at least in general, right? So if you think of first of all the group whose closure we take, so Fn, this expression here, Fn for n in, hang on, for n in Z is a group, right? And we take the closure of this group in this particular topology. Fn is an abelian group. It is well, it is a topological group, obviously, because well, it's the integers, right? And so it has all the nice properties that you would possibly ask for. But if you go over to the closure of it, you usually lose these properties. Now this happens. Sorry for that. Okay. What we can always say is, first of all, that E being the closure of something in the product topology of the compact space to itself, E being the closure in the space, it's certainly a compact set, and it's also right topological. That is, if you take multiplication from the right, this is still something continuous in this semigroup. But this is all that is true in general, and I want to show you this with a very simple example. This example won't play any role in later parts of this talk, but I just want to show you that, well, taking the closure in this topology easily screws up everything, even if you take very simple dynamics. So what we have here is a map on the interval, right? And if you take a look at a particular orbit, this one that I drew here starts at this blue point, right? Then you take the image of that and the image of the image, etc., etc. So what happens here is, whatever point you take, unless you take the point 0, it will approach to the point 1 if you iterate the map F forwards in time. And if you iterate accordingly, if you iterate the map F backwards in time, every point different from 1 will eventually approach the point 0. Okay, this is what happens. And accordingly, it's easy to convince yourself that the LS semigroup looks like follows. Of course, it has to contain, well, this should be an F here. It has to contain all the iterates of the map F, clearly, because it's the closure of those. And well, if you take the closure, there are basically just two options. Either you go for arbitrarily high n, or you go for arbitrarily small n, okay? And if you do this, you end up with either of the two following maps. Either the map eta 0, which maps everything to the point 0 other than the point 1, or the map eta 1, which maps everything onto the point 1, everything other than the point 0 to the point 1. And then if you look at this, you realize, okay, this is not a group, first of all, because eta 0 and eta 1 are not bijective anymore, and it is not an abelian group, and not an abelian semigroup, and it's also not left topological a semigroup, right? So only multiplication from the right is really continuous here. So already in this very simple example, everything that could possibly go wrong from the perspective of a group or a semigroup actually goes wrong. Okay, so this is what I want to say with this example. Now you can basically forget about this example. There's a more important example for this talk, namely minimal and Accu-Continuous systems. Okay, minimal we have already defined. Minimal systems are systems where every orbit is dense. Now, an Accu-Continuous system, I will show you an example in a second, but think of a rotation for now. And actually, this is all there is. So if a system is Accu-Continuous, then it turns out that this LS semigroup is not just a semigroup, it's a group. No, it's also a compact topological group. It's always compact, so I should really add here, it's a compact topological group. In other words, the group operations are really continuous. And at the same time, and this is really nice, the dynamics of the original system are conjugate, so they are topologically the same, like a rotation on this group. And what do I mean by rotation? Well, we have a group operation, as we have an abelian group. I just denote this by plus, okay? And we have a designated element eta, okay, in our group E, so that we define a map on the group E by sending each point Z in E to the point zeta plus eta. Okay, and this is what you would refer to as a rotation. And as I said earlier, just think of an irrational rotation. Irrational because we want a minimal system, okay, and well, rotation because this is really what happens on the circle, right? If you consider T1 R over Z, then well, the rotation is nothing but you send a point X in the space to X plus some angle, say eta. Okay, just that in general, this compact topological group that we end up with, this group E here, that this group is not necessarily just the circle, but it may also be an odometer, and this is what I will explain next. Okay, so what is an odometer? These are actually those minimal Accu-Continuous systems which are important for us in this talk. So an odometer is, first of all, it's defined on a sequence space. Okay, so we have some, first of all, we have some sequence of integers greater than 1. Okay, and then we take the product of these sets. Okay, we call this Zn, where the n here refers to the sequence that we start with. So we have a product of a countable product of finite sets. So this is certainly something compact. Okay, and while we equip this set Zn, this set Zn, we equip this with coordinate-wise addition, right? We have finite sets there, so we finite sets of numbers there. We can certainly define addition there, but then of course, if we go too far, we have a carry and we carry this to the left. So let's write this down for a particular example. If an element Z in our space Zn, well, we always write them as left infinite sequences in this particular case. I will explain in a second why. So if we have such a left infinite sequence and we add the sequence, well, which is 1 at the first position and then 0 in all the other positions, then this is nothing but writing Z3, Z2, Z1 plus 1 in case Z1 is, well, not n1 minus 1. And if it is n1 minus 1, well, what we get then would be Z3, Z2 plus 1. This is the carry, right? And we would get a 0 here. And then it depends on whether Z2 is n2 minus 1, etc., etc. But this is what happens when it comes to addition in this group. Okay, so this is equipped with coordinate-wise addition with carry to the left. This set here is a group, and on this group, it turns out that addition by the element 1, which is just what I wrote down here, that this defines a minimal system, right? And it's really exactly a minimal system of this form, so it's a rotation on this group in this terminology. Okay. And just one word, why do I write this as left infinite sequences here? Why not right infinite? What would be usually the choice? Well, the thing is, you should really think of this as a compactification of the integers, right? And if you think of the integers, how do you usually write down integers? You usually write them down in base 10 representations. So you would like to say, I don't know, right? This is how you represent integers. You have 3 times 10 to the 2, 9 times 10 to the 1, and 5 times 10 to the 0. And this is what happens here, just that, well, we don't have one fixed base potentially, but maybe like different bases on each scale. But then in the end, if we have a sequence which is 0 almost everywhere and just on finitely many entries different from 0, then the sequence actually really represents an integer. And this is how you should think of the space Zn. It's a very natural way to compactify the integers, and the exact way of the compactification that we consider really depends on this sequence here. Okay, but the good thing is, in this talk, what is actually interesting for us will be one very particular, just for the sake of an example, one very particular odometer, where these nk are given by powers of 3, right? So this is the nothing but the product of the map 0, 1, 2 with itself, the infinite product of this set with itself. So in other words, sequences infinite sequences with entry 0, 1, or 2. Again, with coordinate-wise addition and carry to the left. Are there any questions so far? No? Okay. So we saw earlier already with this very simple example of this interval map that basically everything can go wrong with the Alice semigroup, and in general, it's actually quite a nasty object. As easy as it is to define, as complicated it is to compute in specific examples. So in order to understand a system, one would be inclined to study, like to go to its semigroup and then just do algebra, right? One might be tempted to do that. The problem is that typically the Alice semigroup is too ugly, or quite often it is too ugly. And there's a nice dichotomy, between kind of nice Alice semigroups and very ugly Alice semigroups. So the very nice semigroups are, for example, those of minimal Accu-Continuous systems, right, where they are actually groups. Or more generally speaking, are so-called, the semigroups of so-called tame systems, which are just semigroups whose cardinality is not bigger than that of the real numbers. Okay, so this is kind of a nice situation, and then it turns out that if the cardinality of the Alice semigroup is not bigger, not small, if the cardinality of the Alice semigroup is bigger than that of the reals, it is, well, of course, it's next cardinality, but then it is actually as big as it, topologically speaking, could possibly be, because it contains a copy of the Stone-Check compactification of the natural numbers, which is the biggest compactification that there is about of the natural numbers. So it is as big as it could possibly be. Either it's as big as the continuum, or even smaller, or it is as big as it could potentially be, because in the end it will always be a compactification of the integers, right? Because it's a compactification of the set f to the n, where n was in z. So it's always a compactification of the integers, and it always contains the copy of the biggest possible compactification, if it is not of the cardinality of R or less. Okay, and in general, this is a very nice dichotomy, but in general, it's very difficult to use this dichotomy to prove if a system is tame or not. So what is usually used to, and in particular in the case of subshifts, very handy, is an alternative characterization. So before we go to the characterization, let's take a look at the definition of a subshift, because I haven't mentioned them yet. So first of all, what is the full shift? The full shift on two symbols, 0 and 1, on two symbols 0 and 1, would be the map, well, defined on all the, say, one-sided infinite sequences in zeros and ones, right? Equipped with the product topology, and well, this map just shifts according to this rule, right? It just shifts a given sequence one position to the left. Okay, this would be the full shift. And a subshift is any closed subsystem of the full shift. So if you have a set of 0-1 sequences, which is closed and invariant under shifts, okay, then this defines a subsystem of the full shift, and this subsystem is referred to as the subshift. Okay, now coming back to the notion of tameness, if we are given a subshift, it turns out that this subshift is non-tame, even only if there is an independent sequence. Okay, there are lots of sequences around. This is a bit annoying, but unavoidable. So there is an independent sequence. In other words, a sequence of times, or if you want, indices, such that for every 0-1 sequence, well, there is some sequence in our subshift, which, if we read the sequence along this independent sequence, along this specific times ti, it reads exactly as the sequence phi, right? It reads exactly as this sequence phi, which was arbitrary, an arbitrary sequence in zeros and ones. In other words, no matter what our subshift looks like, if it is non-tame, and well, when there exists a sequence of times, an independent sequence, so that if we only look at the entries that we see along this independent sequence, we actually see the full shift again. Okay, so one may summarize this fact as this is the wrong computer. One may summarize this fact by saying a subshift is non-tame if and only if it embeds the full shift in the above sense. Okay. Yeah. Okay, any questions so far? No. Okay, then what this talk is about is, well, a result about the tameness or lack of tameness, the non-tameness of certain subshifts. And before I formulate the result, or at least the corollary of this result, I want to look at a very specific example which is covered by this result. And we'll discuss why this example is an example of a non-tame subshift. And well, it's not a very complicated proof, but it's a combinatorial argument, and we only have like 20 minutes or something. So I assume, at least if I would listen to this, I would get lost at some point. Okay, so don't get frustrated with it. The only idea here is I want to show you. Well, I want to get you to understand like the gist of the arguments, just to see. Okay, it's a very combinatorial, but not like it doesn't involve any heavy machinery argument, which gives us the non-tameness of the examples that are covered by all theories. Okay, let's take a look at this specific example. So this specific example will be a subshift. In particular, it will be a substitutive subshift. So what is this? It's a subshift which is defined through a substitution. And well, what's a substitution? This is what we see here. Substitution is a map on an alphabet, and I will, for the sake of completeness, I will just stick with the 0-1 alphabet here. So substitution is a map which maps the letter 0-1 to words in 0 and 1. And the particular example that I would like to look at here is, well, this map here, right? The map which sends 0 to the word 001 and 1 to the map to the word 101. Okay, so initially a substitution is only defined on letters. Okay, but then it's obvious that we can extend this definition to words by just coordinate-wise application. So we apply the substitution to this letter, then to this letter, and then to this letter. So if we iterate the substitution twice and apply to the map to the letter 0, what we get is the upper word 001, 001, 101, 010, 010. And if we apply twice to the letter 1, we get the words in the lower line. Okay, and what you see here, and this is an important property of this particular substitution. Well, if you apply the substitution to the letter 0 or 1, well, the images coincide on the first letter, right? And due to this, the next images of 0 and 1, they will coincide on the first 3 letters. In fact, actually on the first 4 letters, because but okay, this is not so much the point. The point is the successive iteration of the map theta. Well, lets the words that we get coincide on bigger and bigger prefixes. Okay. Now, just like we can apply the substitution not only to letters but also to words, we can actually trivially extend it also to sequences. Right? We just apply the substitution to every entry of our sequence, and with this property that we just saw, that the successive iteration of the substitution results in bigger and bigger prefixes where the images of 0 and 1 coincide. With this property, we see that the substitution on the space of all 0-1 sequences is in fact a contraction. Okay, and a contraction on a complete metric space always has a unique fixed point, and well, this unique fixed point, well, it looks somewhat like this, and well, I can't possibly draw all the entries of the sequence. But okay, we have this uniquely defined point associated to our substitution. Then what we do is we shift this point, okay, by all possible natural numbers, take the closure of what we get, and what we get is something closed, because we take the closure, and it is something which is invariant under the shift, because the shift is continuous, and we took the closure of something with a shift invariant by definition. So what we have is actually a subshift. Okay, in this particular example, it's a substitutive subshift associated to what is also referred to as a constant length substitution, constant length, because no matter to which letter you apply the substitution, the length of these words is always the same. In this case, it's 3. And what I want to show is that this particular substitutive subshift embeds a full shift. In other words, that this particular substitutive subshift is non-tame right? And we have to show, therefore, that there exists an independent set, an independent sequence for this subshift. And in order to do this, we will make use of, well, 3 facts. The first one, none of them is a tough fact. The first one is something which I won't be able to prove, but it's also nothing too difficult, and it's also well-known and a classical fact. So, first thing to note is, well, if X sigma is our subshift, our substitutive subshift, then it turns out that this is an extension of an odometer, right? And this was the odometer which I showed you earlier. The odometer, the space of all left infinite sequences with entries 0, 1, or 2, with coordinate-wise addition, right, and carry to the left. So this is the space, and the dynamics on the space was we just add 1 to the sequence. Okay, so it turns out that our subshift is an extension of this odometer. Okay, and the nice thing is not only that it's an extension of this odometer, the nice thing is also we can very nicely characterize this factor map, pi. Namely, if the point X maps onto some sequence with some entries, in this case of this kind, then it turns out that X lies in this set here. Okay, what is this set? Well, theta is a contraction. Okay, so the more often we apply theta to the n, to the space X, the smaller this set here gets. Okay, so say our subshift is something like that, and we apply theta, I don't know, n times to it, then we have only this little small box left. And it turns out that, well, this box, if we shift it, this gives us a disjoint set. If we shift this again, we get again a disjoint set, etc., etc. And if we shift this whole thing, say this is, say we have done this only, well, and we did this for the case theta to the 3, and I erased the last, sorry, this one I want to erase. So we did this for theta to the 2. Then it turns out that, okay, we can do this exactly 3 to the power of 2, so 9 times, until we come back to the original sets. So what we get is this theta to the nx gives us a set, which by applying the shift to it, gives us a natural partition of our subshift, okay, of our space X. So the big thing is X, and the small thing is theta to the X in this particular case. And well, our factor map is of such a kind that it tells us in which shift, so in which partition element, in other words, of this natural partition that is associated to our substitution, in which element of the of this partition our point X lies. Okay, so it's a very explicit characterization of the factor map between our substitutive subshift and the triadic odometer. Okay, so this is one fact. Again, I won't prove this. Another fact, which is actually easy to see, is the following commutation relation between the shift and the substitution. And well, we are not going to prove this for n, but you will understand it once you understand it for n equal to 1. So say I apply, the shift. Let's start on the left. Let's start on the left. So we apply the shift to, say we have a sequence which starts in 0, 1, 0, 1, 0, and then we don't know what happens. We apply the shift 1 time, okay? So we shift, this is the new position, we forget actually about this one, and then apply our substitution. What we get is, well, what is the image of this word under the substitution was exactly this word. So it's the same as first applying the substitution, right? If we apply the substitution to the whole thing first, we get this entire word and forgetting about the first 3 entries, okay? This is exactly what this commutation relation is telling us. And yeah, I hope you believe me that this holds for all n, and now that I showed you this argument. So this is a very, very basic fact. And there's a third fact, which reads a bit strange, and yeah, well, it's something which is specifically given in this particular situation only, but it's also nothing hard to prove now that we know these 2 things. So suppose we have some point x in our subshift whose image under the factor map, right? So this is our sequence x0, x1, x2. If we project it down to our odometer, we assume that the first time we see a 0 in, like looking from the right to the left, right? This is how we read the sequence. The first time that we see an entry equal to 0 is at position Zn. Okay, just assume we have such an, well, of course there is such an x, and all the other x are not interesting for us for the time being. And all the other entries that we have here are either 1 or they are 2s, right? This is all there is. So this is a possible image of the points we are interested in. Okay, if this is the case, then it turns out that x0, so the first entry, we can compute it. The first entry of our sequence x is determined by whatever happens here in those first entries different from 0. Namely, we just have to count the number of times that we see a 2 here. So in this particular case, we see 2 2s. So here this would be, in this example, it would be 2. Then we mod by 2. So this is 0. Okay, so in this particular case, we would see that the first entry equal to 0 is just 0. Okay, and I will show you the proof. I won't go through the details because it's more confusing than enlightening, but I will show you the proof nonetheless, just so that you believe me that it's actually simple, because it's basically just 2 lines. So how could we possibly prove this? Well, we make use of equation 1, right? We know that x lies in this set. So this is what we write down here on the left-hand side, right? Then we use successively this commutation relation, okay, to end up with an expression of this form. And okay, then what we have here is we apply the map theta, the substitution theta, to our space x. Then we shift by Zn. Okay, Zn is 0, so this is actually no shift at all, but then maybe we shift by Zn minus 1. But whatever we shift by, it's always either by 1 or by 2. So we apply our substitution theta, which gives us, well, at the beginning, it gives us actually the word 0, 0, 1. Then then we apply theta again. So again, we have the word 0, 0, 1, and then we shift by either 1 position, which would bring us here, or we shift by 2 positions. Okay. Now, if we shift by 1 position after applying the substitution, we actually get the same letter that we started with, right? If we go from 0 to its image and then shift by 1, we end up on 0 again. And if we start with 1, apply the substitution and shift by 1, we end up with 1 again. So whenever we see a 1 in one of these entries here, or likewise here in these entries, whenever we see a 1 there, we don't change the symbol. And whenever we see a 2, what happens is, well, we apply the substitution and then go to the second position. So if we start with 1, we get 0, and if we start with 0, we get 1. So whenever we apply, whenever we see a zi equal to 2, we swap the letter, okay? And this is exactly what is written in this, here in equation star. We count the number of occurrences of 2s, okay? Then mod by 2. So we count the number of times we swap the symbol. And well, if you swap by an even number of times, you haven't swapped at all. And if you have swapped by an odd number of times, you have swapped by 1. Okay, well, I admit that I would still need to think a bit about why this is really true, what I said, but I hope that you just believe me that this is basically the idea. There's really no magic, okay? So summing up, what we have is we have the substitution defined as above, and we have this property where I kind of discussed the proof a minute ago. Okay, and again, we want to show that the associated substituted subshift is non-tame. So we have to show that there is an independent set, okay, an independent sequence, a sequence of times along which we can realize every possible sequence in zeros and ones. So the first thing we do, or that I will do, is I will write down this independent sequence, okay? So it's just a sequence of numbers, and at the moment it doesn't make sense why I chose this particular sequence. So it's a sequence defined like this, right? And I told you earlier that basically thinking of odometers is nothing but thinking about the compactification of the integers. So here you can easily see the number 3 would be in in base 3 representation would be the number 1, 0, right? So this is really the sequence which is 0 everywhere, only in the second position it's 1. And then etc. etc. In the same way, the thing is, we define these times, we define them in such a way that they are always 0 on the odd position and always 1 on the even positions. Okay, this is the only important thing that we will use in the remainder of this proof. Okay, but for now it doesn't make this. It's just an arbitrary choice, which just happens to make sense in the end. Okay, so now for this to be an independent sequence, we need to show that for every 0, 1 sequence, well, we find a sequence in our subshift which realizes this 0, 1 sequence along these times TL. Okay, so give us some, like, take some sequence of zeros and ones. Okay, so we call this phi again. Then we define an auxiliary sequence alpha, again in 0, 1, it's just another sequence, unfortunately. Okay, we define this such that this equation holds. And why should this be always possible that this equation holds? Well, for L equal to 1, it's certainly possible. We just choose alpha L equal to phi L. Okay, and well, for any bigger L, well, if L, say we have to find our alpha up to alpha L, then, well, if phi L is the same as phi L plus 1, alpha L plus 1 just has to be 0 because we don't want to change anything. And if it is a different value, well, alpha L plus 1 is 1. Okay, so it's always possible to define this auxiliary sequence alpha. Okay, so unfortunately, this is not all the notation that we have to make use of. What we want to do is we want to define a point Z in our odometer in the factor, such that all its preimages, right, all the points X in its preimage, all its preimages realize the sequence phi L along this set of times that I just defined up there. Okay, this is what we want to show. And this point Z, how is it defined? Well, it's defined through these numbers I0 and I1. So I0 is just 1, I1 is just 2. Okay, and well, the index, so we basically our sequence Z in the odometer is always 0 on every even position, and on every odd position it may be 1 or it may be 2, depending on the respective value of the auxiliary sequence alpha. Okay, so far this is just definitions. It's confusing enough, but it's just definitions. And now we are going to see why this is really doing the job. So first thing we note is if we add a time TL to this point Z, well, it's really nice, really easy to do this addition here because addition is coordinate-wise, right? But the TLs are just defined in such a way that every odd position is 0, and Z is just defined in such a way that only the odd positions are different from 0. So basically, we just have to fill in the zeros, fill in the gaps between the I alphas with ones, well, up to the point L, up to the point alpha I alpha L. Then we have the last one, and from then on, well, it just looks like the sequence Z before, right? Okay, the nice thing now is this expression Z plus TL is now an expression of the kind that we actually understand by means of this equation star, because this is an expression where we know where the first occurrence of a 0 is. It's here, right? Because every even position is a 1, and I alpha 1 or I alpha 2, etc., can only assume the value 1 or the value 2 by definition of I. Okay, so this is a sequence which we can treat by means of this property star. Okay, and this is just some computation which in a minute makes sense. So we see that the number of occurrences of the entry 2 in this sequence, well, where can a 2 actually occur? It can only occur on the odd positions, right? Because every even position is filled with a 1 or with a 0. So the number of occurrences of a entry 2 in the sequence, well, it equals the number of occurrences of situations where we have a 1 in our entry, in our index of the I, and we always have a 1 in the index of I if, well, the respective alpha I is 1. So basically what we do is if we want to know the number of occurrences of 2s, in the sequence, we just sum up our sequence alpha, our auxiliary sequence alpha m from 1 to L. And by definition, well, this is just magically, by definition, it coincides with phi L mod 2. Okay. Okay. Now, if you, well, I think I will spare you the rest. I hope you believe me now that by means of this equation, we can easily compute the entry of the sequence X at position TL and realize that because everything is defined the way it is defined, it really coincides with phi L. So the sequence X really realizes along the sequence of times TL, it really realizes the sequence phi. And as this sequence was arbitrary, we can realize the whole full shift along these independent sequences. Okay. Again, it's a combinatorial proof. They don't make sense until one understands them. But at least you see, okay, there's not much magic. It's something which is really hands-on. Okay. So I summarize this. This was the situation. We have a subshift defined by substitution. And well, we had this maximal Accu-Continuous factor. I didn't mention this notion. It's just, well, we had this factor map from our subshift to some Accu-Continuous system, which is maximal in a certain sense. Okay. And we realized that the associated subshift is non-tame. And this actually turns into a theorem of much higher generality. So let theta be any primitive aperiodic substitution of constant length. So what is that? Well, first of all, it's a substitution on arbitrary alphabets. I only discussed 0, 1 alphabets, but actually you can take any finite alphabet here. Okay. It's a constant length substitution for the same reason as this one here was a constant length substitution. No matter to which letter we apply the substitution, the word that we get always has a fixed length independent of the letter. Okay, this means constant length substitution. Aperiodic means that the point, the fixed point of our substitution, there may actually be several, or they will be actually not necessarily fixed points, but anyway, say the associated fixed point of our substitution is not a periodic point, because if it's a periodic point, the subshift that we generate is also a periodic subshift. It's boring. It's a finite space, so there's nothing going on. So we want a substitution which generates interesting dynamics, hence aperiodic. And well, primitive, well, it just means that the subshift that we generate, like here, that the subshift is really a minimal shift. Okay, so assume we are in this situation. We have a substitution which generates a minimal subshift which is not periodic. Then this subshift is tame if and only if theta has a coincidence and the maximal Accu-Continuous factor contains only finitely many orbits, only finitely many singular orbits. And well, I can't explain you what this really means. Like in general, if you don't know what it means for a point to be singular or not, this would go a bit too far here. Well, actually, it's not so much. It's basically those points in our factor whose pre-images are not singletons, right? These are the singular points. And if you only have countably many of them, then your system is tame, the subshift is tame, otherwise it isn't. Now the thing is, it seems like a very abstract condition, but it's actually really easy to decide. Given a substitution, there's always, like, if it is a substitution on a bigger alphabet than just 0, 1, there's a straightforward algorithm to decide. And if you have a 0, 1 substitution, it's super easy, because you just take a look at the image of 0 and the image of 1. And well, in this particular case, we have two positions where these images don't coincide. Okay, and this is all that you have to check. If there are 2 or more positions where the image of 0 and 1 don't coincide, then the subshift is non-tame, otherwise it is tame. Okay, for higher alphabets, it's a little bit more complicated, but it's also quite similar. Okay, I guess I'm running out of time, right? I should finish here, or how is it?
No, I mean, you can, there's no hurry to finish.
Okay, then I will briefly sketch how this theorem can be extended actually to quite a bit. And in order to do this, I will briefly sketch discuss what is a Bratelli-Virchow representation of a minimal symbolic system. And well, I'm afraid that if you don't know what this is, it's maybe a bit hard to follow this, but I will still briefly explain what this is. So it turns out that every minimal dynamical system on the Cantor space, or in other words, every minimal symbolic system, can be represented by a Bratelli-Virchik diagram, okay? And what's a Bratelli-Virchik diagram? It's exactly what you see here on the screen, okay? You have these different levels of, at each level, finitely many edges, okay? Well, it's an infinite diagram, so this has to be continued. And, well, only vertices of consecutive levels are connected through edges. Okay, this is essentially what a Bratelli diagram is. Now, you can now put like an order. You can easily define now dynamics on this diagram. And in order to define these dynamics, you first define an order, or say a partial order, on the space of infinite paths in this diagram. Okay, first you define an order for all the vertices of which end in a given. Sorry, for all the edges which end in a given vertex. Okay, so say we are interested in the vertices, in the edges which end in this vertex. So these are just these two edges. Then, well, we just say, okay, well, we just put some order on these edges. Okay, say this is 0 and this is 1. Okay, and we do this for every vertex. For all the edges which end in some vertex, we define an order. Okay. Now this order then naturally defines an order on
Gabriel.
Yeah.
I think I cannot listen to you. I don't know if. Now I can listen again.
Okay. Okay. Now this order, which initially is just an order on the edges which end in a given vertex, this can be easily extended to an order on finite on all the finite paths which end in a given vertex, right? Can say, okay, then you do this with lexicographical order. You extend this to an order on all the graphs which end in a given vertex, and like this, you can extend it to a partial order on infinite paths by saying, okay, two paths are comparable if at some point they go through the same vertex, like these two paths, okay, and then, well, you just consider the heads of these paths, right, and compare them according to the lexicographical order, and well, this gives you a partial order on the infinite paths. And well, the successor map associated to this partial order, this defines some dynamics on this Bratelli diagram. And it turns out, and I don't want to go into the detail, I just want to sketch briefly the ideas. It turns out that every minimal symbolic system, every minimal dynamic system on the Cantor space can be represented by a Bratelli diagram with an associated order on its edges. Okay. And okay, well, then the next statement, forget about this definition that I wanted to give here. It's a statement which goes back to Gabriel and Johansen, which characterizes a certain class of shifts, so-called tuplet shifts, and says, okay, well, while every symbolic minimal system can be represented by some Bratelli-Virchik diagrams, the class of so-called tuplet shifts, whatever they are, it's quite a big class of systems actually, can be characterized as those shifts which allow for a Bratelli-Virchik diagram with an equal path number property. That is, on each level, if you take a look at the vertices, the number of edges which end in the given vertex is always the same, right? On this level here, we always have two edges ending in a vertex. On the next level, it's again same. Well, it could also be, say, we have 3 here, okay? The exact number doesn't matter, but in each vertex on every level, you have the same number of edges entering this vertex. Okay, this is an alternative characterization of so-called tuplet shifts. Whenever you have such a representation, your shift or your system is a tuplet shift. Okay, and this is where I wanted to end, just to show you that this theorem about substitutions can be extended if you have such a Bratelli-Virchik diagram where, well, you have this equal path number property, so you represent a tuplet shift, and at the same time, the number of vertices on each level is uniformly bounded. Okay, so there's a number k, so that on no level there are more than k vertices. Then again, the associated tuplet shift is non-tame if and only if the singular points in your maximal Accu-Continuous factor are countably many. And if they are uncountably many, then the associated tuplet shift is actually non-tame. And the idea of this proof, well, it's well, one cannot. Well, the proof that I talked about, one cannot really extend to this particular setting. But in a way, there's well, starting from there, one could possibly get there. So it's kind of inspired, at least, by this much simpler case of the 0-1 substitution that I discussed earlier. And well, this is where I wanted to stop. Thank you.
Well, thank you for your very nice talk. I don't know if there's anyone with some questions for Gabriel.
I have yes, some questions.
Okay.
So for I have so for the finite. So I was looking at your paper that when you define the finite rank, but on the special Bratelli diagram where you have the same number, right?
Yeah. It's well, I would like to erase this. Yeah. So given some diagram like this, we say it has like a finite tuplets rank if it is of equal path number property and has finite rank. So it may well be that there's a tuplet shift, so a shift which allows for a Bratelli diagram which has the equal path number property, but none of these diagrams which have the equal path number property are of finite rank. It may be, it may not be, we don't know actually. So it's not clear if this is the same as saying it's a tuplet shift of finite rank.
Okay, yeah, I lost connection, but I heard the answer at the end.
Okay.
And my other question is, do you think there's hope to get also a nice characterization like this, but for embedding only finite portions of the full shift?
So what do you want to say, like that's
so sorry, I'm having problems with my internet.
I'm not sure if it's my internet actually.
No, I think it's mine because it even kicked me out.
Okay.
What I want to ask if you think there's any hope to characterize null systems.
Yeah. I didn't really think about that. So, well, I think in this particular, at least for the substitutions, I guess that it's the same for substitutions. That should be the same, being null or tame. I hope I'm not lying now, but I think in this specific case, it's the same. And I think, and then maybe it also extends to the case of tuplet systems, of finite tuplets rank.
Yeah.
I don't know. I never thought about that, but I also think that beyond this, I don't know. I also didn't think about this, but I think beyond that, everything is possible, and such a nice characterization wouldn't really exist anymore.
Yeah.
Also,
but have you? I mean, in your proof, maybe you could. Maybe this characterization is inside your proof.
Yeah, exactly. Maybe it's already there. Yeah, but
maybe it's already there. Yeah.
I would have to check. Yeah.
Mm-hmm.
And also, it's important to know that this really just, I mean, it's not just that we couldn't do better, like by relaxing the condition of finite tuplets ring, but we also have examples which show, like, as soon as you don't have finite tuplets ring, basically everything is possible. So, yeah.
Right. Well, there's a comment in the chat asking whether you could share with us your slides.
Presentation.
Sure. I can send them to you or to Felipe afterwards.
Yeah, that should be great. I have a question. Well, I think it would be like rather really elementary, but Can you provide an explicit, well, an example of a tuplet sequence which is not periodic?
Yeah. Okay. Sorry. I mean, I should have done this. So first of all, here's the definition of tuplet sequence, right? Every index appears periodically, and then the way you can basically construct any tuplet sequence is by you just put your periods as you wish. Say we start with some 2 periodic entries. Say every second entry should be, or every odd entry should be 0. Okay, and wherever I put the space, I don't want to define the sequence yet. Okay, we define now a sequence in stages. Okay, and you know how this is continued. Okay, this is the first stage. On the next stage, I fill the gaps, but I should of course not fill all the gaps, because then I would end up with something periodic. But I say every odd of the remaining gaps I fill, this time with a 1. Okay, etc., etc. And this is the second stage. On the next stage, I do the same again with every first of the remaining gaps. This time I put a 0 again. Okay, and you do it like this. Then you end up with something where every entry is actually periodic, and you have to think a bit about. But you can see, okay, this can never be periodic as a sequence. So it's just every entry there. And like this, you can actually construct all the tuplet sequences, because again, well, there is, for each entry you have some period, so you can start with arbitrary periods and fill the gaps like you wish. Yeah.
Oh, okay. Thank you very much, and that brings me to a new question. Is so so this tells us that tuplet sequences are not that I just forget the name, but if you have like one of these exponents from a combinatorial perspective, exponents of repetition and all of this that measure somehow how complicated these sequences are, then tuplet sequences are not that complicated, right? In the sense that they have a nice structure.
No, they can be very. I mean, they can have positive entropy of value arbitrarily close to the entropy of the full shift. So they can be very chaotic in this sense. There's almost no restriction. The only restriction there is, and this is basically by definition, not by this definition, but by an alternative definition. You always have an odometer as a factor, okay? And there's at least one point in this odometer whose pre-image is a singleton. Okay, this is the only. They are so-called almost automorphic extensions of odometers. This is the only restriction there is. But other than that, you can. I mean, not everything. They cannot be weakly mixing because they have an Accu-Continuous system below, right? But given this restriction, almost everything else is possible.
All right. So
it's a huge class.
Mm-hmm. Yeah, I was thinking that maybe if we could say that tuplet sequences are well, if there's actually some relation between tuplets and automatic sequences, but what you're telling me there's not.
Automatic sequences as sequence. Well, now I have to. What is the automatic sequence? Sequence whose language can be accepted,
generated by finite automaton or the fixed point of morphism, like the one you build with the theta.
Well, these are always tuplet sequences. These fixed points of the morphism, like of substitution. Not always, but like the one I showed you was a tuplet sequence. Okay, and there's like if you have a constant length primitive substitution with a coincidence, it's always a tuplets. It's always a tuplets. Well, if I think of languages which are accepted by an automaton, you have the pumping lemma, right? So you can get arbitrarily big, like there's given the number of states of your automaton. There's like at some point you always get this. There are words, there are loops. That's it. There are loops in your automata, and then you can loop around as often as you want along the loop until you like go wherever you want. And these kind of loops, they don't exist in aperiodic substitutive subshifts. So in this, I would say that that the language associated to Untitled Shift is not accept. It's not the language which is accepted by an automata. But I haven't really thought of it.
All right. Well, thank you. Thank you. I don't know if anyone else has some questions to Gabriel.
I have one question for Gabriel. Thank you, Gabriel, for the talk. Can you hear me?
I can hear you not perfectly, but I think I can hear you enough.
Okay. There, is it better?
Much better. Yes.
Okay. Well, thank you for the talk. I was looking at the condition, the finite tuplets. So I think those have a non-superlinear complexity, meaning that the complexity along a sequence it behaves like linear.
The substituted subshifts definitely have linear complexity.
Yeah.
For finite rank, I think there is some relation, but I think it goes like every sequence, like every shift with linear complexity is of finite rank, but I think the opposite is not necessarily true.
Right. But I think that if you have a tuplet of equal path number, then the complexity is non-superlinear, meaning that it's sublinear but along a sequence, not all. Not for all.
I don't know, to be honest. I don't know, but it sounds reasonable.
Yeah, actually, I was going to ask if you impose that the tuplet is sublinear.
No, it's not. We don't have any extra assumption on it. No.
Okay.
No.
But if you impose something like that, do you think it's more like?
Instead, no, I get it. Instead of the equal path number property.
Yeah, because equal path number property implies non-superlinear on a sequence.
Sorry, no. If you ask for like not superlinear growth instead of finite tuplet rank.
Yeah, well, that could be one.
Yeah, this might make sense if it's not the same, right? But I have to pass. I'm sorry. Yeah, I cannot tell. Sorry.
Thank you.
Thank you.
Thank you. I don't know if there's any other question for Gabriel. Well, if there are no more questions, I just want to thank Gabriel and all of you for coming today, and especially Gabriel, because the talk wouldn't have been possible without him.
Thank you.
Well, yeah, thanks a lot, Gabriel.
Thank you very much.
Hopefully one day you can visit.
Oh, yeah? Yeah.